Today we're going to be looking at a heavily requested channel, Sabine Hossenfelder. She's a physicist that makes a lot of science-related videos. We're going to be looking at, is nuclear power really that slow and expensive? Well, given the thumbnail says false, I'm thinking she thinks no. Well, it certainly was for Vogtle 3 and 4 in Georgia. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's get right into this.
There are many bad arguments against nuclear power. For example, that it'd just be too simple a solution to climate change. We need to make the...
What? I've never heard it phrased quite that way, but a bad argument saying it's a too simpler solution. Well, as an engineer, I'd want a simple solution, but climate change is a fairly complex issue. I've never actually heard that something would be too simple of a solution, meaning something that we should not pursue. That's interesting. If it were that simple and I was king of the world, it would be a no-brainer. But I've never heard that particular argument.
Difficult and painful. That's not a good argument because it's not actually that simple to prevent further global warming, even with nuclear power.
True, though. Again, I've never heard of that. Maybe it's more common in other countries, but not within the U.S. anyway.
There are two good arguments against nuclear power. It's too expensive, and the power plants take too long to build. But are they true? And if so, why is it that nuclear power is so slow and so costly?
Those two are actually kind of the same argument because you're looking at time value of money, basically the net present value of your investment.
That's what we'll talk about today.
About the what?
Before we talk about cost and speed, let's quickly go through other common arguments against nuclear power, just so you know why I don't think they're good arguments. The most common argument against nuclear is that nuclear waste is such a big problem. But in truth, there's very little nuclear waste. Because nuclear power has such a high energy density, you need little fuel to create energy with it. And consequently, there's little waste. Most of the waste is only mildly radioactive, and what's left can be recycled or buried.
Yeah, so nuclear waste there's a bit of a misnomer about the different types of waste. Like a lot of it is just straight up recycled on site. Some of it, the low level waste, is basically doing your laundry because it's like contaminative protective clothing for people working in radiological controlled areas. The medium or intermediate level waste is from things like spent resins for purification loops in a reactor coolant system, which the solution is leave it on site to decay away for days to months. And the high level waste is the main one that everyone is concerned about. But by volume, all the nuclear waste, all of that ever produced by the United States would fit in one football field. How very American of an analogy. For those of you who don't know, an American football field's a little less than 100 meters across.
The numbers about nuclear waste in a previous episode. American commercial reactors have only generated about 90,000 metric tons of spent fuel since the 1950s. That could be fitted onto a single football field at a depth of less than 10 yards. Doing this would have the added benefit of mutating football players to grow more legs, which would...
What? That's hilarious. Grow more legs. I was just expecting them to get big and strong like the Hulk. And hey, we could save the football industry money on steroids.
The sport considerably more interesting, but I digress. I get often asked, yes, but would you want to live near a nuclear waste deposit? To which the honest answer is, it wouldn't bother me at all. Another bad argument is
You say waste deposit, so the high-level waste are stored in dry casks. I've done a few, for those of you who haven't seen my other videos on the subject, here's what they look like. They're not those scary yellow barrel thingies that are oozing green sludge. In fact, these things are safe, can withstand direct missile strikes and severe weather, and they're safely stored on site of nuclear power plants. So even if we don't find a permanent underground repository, nuclear waste isn't really a problem. In fact, it would be nice if you could just take one of these things, hook a couple of pipes up to it, and it would generate enough heat to take care of your hot tub for millions of years. So no, I don't have a problem living next to them either.
Yes, there have been 2 major nuclear accidents, but if you look at the numbers of deaths and further detrimental health effects, they're nowhere near as high as the number of people who have died in plane crashes.
What's interesting is she says just 2 major nuclear accidents, no doubt referring to Chernobyl and Fukushima. Not even mentioning 3 Mile Island, as much as that one gets brought up in the United States, because, again, it really wasn't a major accident. It was safely contained. Whereas me, being in the industry, was always taught the big 3 being Chernobyl, Fukushima, and 3 Mile Island in that order. And the difference in magnitude between Chernobyl and Fukushima is a factor of 10 on your worst overestimates. And between Fukushima and 3 Mile Island, well, kind of hard to compare something to 0.
And they're basically nothing compared to the deaths we can expect from climate change, which might well be hundreds of millions.
Okay. I can tell she's being silly here with the whole turning it into water world with all the rising sea levels. I guess Kevin Costner would be okay.
Of people. Again, I collected the numbers in a previous episode. Clearly you do.
Oh, so it looks like she does other things on nuclear power. Let me know down in the comments if you want to see me react to more of her videos.
Don't want accidents, and not just because they kind of make bad publicity, but nothing comes without risks. And the risk of further increasing carbon dioxide levels is much higher than that of nuclear accidents. There's no way a nuclear power plant can go so terribly wrong that an accident would kill more people than letting carbon dioxide levels increase. Another bad argument is
And also forget the whole CO2 emission aspect. Even if you think global climate change is a conspiracy theory or whatever, just the toxicity that you would get from coal power plants is far worse. Between 1999 and 2020, well over 400,000 people have died from coal power plant related deaths. So I'm talking members of the public. Forget things like industrial accidents, which are more common in coal than nuclear as well. And that's just mainly from working around a bunch of hazardous chemicals. Nuclear power plants are actually fairly clean to work at. The worst part is it could just get pretty hot. The main condenser in the turbine building can get upwards of 130 degrees Celsius if you were like right on top of it. But considering the only waste product that's emitted or in the non-nuclear, non-contained part of the plant is water, the main hazard is heat rather than contamination or inhaling something you shouldn't be inhaling.
I can't see it, but it can kill me. We can't allow that. Well, you know what? You can't see most pollution in the air, water or soil, so why aren't you running around all day screaming that civilization must be discontinued immediately?
That's a fair argument.
Seems like somewhat of an overreaction. Yeah, the good thing about radioactive pollution is that in contrast to most other types of pollution,
you also can't see ninjas either before they kill
you. Worried about radioactive pollution? Go and buy a Geiger counter. Want to know how many microplastics you're breathing or what's with those forever chemicals in your tap water? Well, good luck finding someone to analyze your samples.
Yeah, so the subject of this video is about cost. Well, let's take a look. Let's see. So Geiger counters, all right, seeing, hey, some results that are less than $100, a few $100. Whereas chemical analysis, some of those sensors can get pretty sophisticated, upwards of $1,000. Also, they're less intuitive on how to interpret, and some things, just depending on what sort of pollutant you're looking for, you need to take a grab sample and have it sent away to a lab to be analyzed, which takes a lot more time, whereas a Geiger counter, it's real-time data that you can observe.
This isn't a complete list of bad arguments. I'm sure you've come across many more. But the accusation that nuclear power plants take a long time to build and are just too expensive to make commercial sense are good arguments. So let's look at those too. We'll start with the long construction time. I'll be talking about the time from the beginning of the construction to the end, not including the planning stage.
Okay, now that's a key point, not including the planning stage. The planning stage can take a long time. Southern Nuclear Operating Company submitted their applications to get a license from the Nuclear Regulatory Commission, the thing that says, hey, you can operate this nuclear power plant, back in 2008. Vogtle Unit 3 came online toward the end of last year, 2023. And this was, I'm going to say, relatively easy based on acquiring the site selection, because Vogtle's 1 and 2 have existed for a long time. And there was enough space for Vogtle's 3 and 4 for that long, and 1 and 2 have been around since the 1980s. This is neglecting the acquire land step. The amount of money compared to construction isn't much, but getting these licenses isn't exactly cheap. I mean, we're not talking we're not talking multiple billions of dollars, but you still have to have your regulatory affairs team, your licensing team, which is an entire department in Southern Nuclear that does these sort of things. And as well as all the resources used by the Nuclear Regulatory Commission. And that's just one aspect of it. That is that specific federal agency that you're working with. There's a lot of steps. There's a lot of other steps between then and breaking ground.
For a typical fossil fuel plant, it takes something between 3 and 4 years. If it's a small gas plant, they can do it in about 2 years. How long does it take for a nuclear power plant? Well, according to this guy who recently left a comment on my Facebook page.
Wow. Calling this person out by name. Okay.
It takes tens of years, and then it'll be 10 times as expensive. Well, maybe you shouldn't trust random guys on Facebook. Though, to be fair, he's a bit on the extreme.
Just calls them out.
The numbers
that's awesome.
that I've seen being thrown around on social media is that it takes a decade to build a nuclear power plant. A typical example is...
I mean, Vogtle Unit 3 started in 2013, so that's exactly where his argument's coming from. Can't really argue that.
This article by Naomi Oreskes in Scientific American from last year. It's titled, New Nuclear Power Plants Are Unlikely to Stop the Climate Crisis.
That doesn't mean we shouldn't build them, though. I mean, yeah, there's no one solution to stop the climate crisis. It's kind of, okay, I would come back and say, all right, new solar plants will not stop the climate crisis. Carbon capturing and sequestering will not stop the climate crisis. I'm not sure exactly where that's coming from.
Article, she claims that globally the average construction time is about 10 years, and some notorious examples have taken much longer.
And here, this article mentions U.S. at Georgia Power's Vogtle plant started in 2013. Vogtle 3 is done. Vogtle 4 will be done in 2024.
Okay, let's look at the source that she provides for this. It's conference proceedings from 2011 with 2 authors. The paper says the average construction time of nuclear power plants between 1976 and 2009 was 92 months or 7.7 years, with a maximum of 10 years between 1996
because people knew how to build them faster back then. There were more of them.
All right, she picked the average from those 4 years where the construction time was particularly long for whatever reasons, and then decided to not tell you about the past 20 years where it's been lower. Okay, so you get anti-nuclear activists claiming it takes 10 years to build a nuclear power plant, but
I actually think some of it isn't anti-nuclear, some of it are just Americans, because that's the only plant that the U.S. has seen built in 10 years that aren't necessarily anti-nuclear. Because, I mean, that's exactly the first thing I thought of just when they mentioned 10 years. It's like, well, Vogtle Unit 3 is the first thing that came to my mind.
How long does it really take? Oreskes wrote something about notorious examples where it took a very long time to build a nuclear power plant. Same problem as with the billionaire's net worth. The most notorious example of a nuclear power plant that took a long time to build is the second unit of the Watt-Bar station in the United States. It took a whopping 43 years from the start of construction to the beginning of commercial operations.
Yep.
Though the construction was paused in between for 22 years, so this number is itself misleading. That was a lot of warnings of how to interpret the data. Now let's see how they look. These figures were...
And that's something that can run into for any large construction project. Could be from changes to who's in office, losses of funding, changing out who your general contractors are. You can see that on any projects. The thing is with nuclear, though, it could just... because nuclear stuff is special, unique, and expensive, and things have to be revalidated by regulators, even during phases of the construction process, it compounds in a unpleasant manner.
By Hannah Ritchie, who does amazing work for Our World in Data. As you can see, the average, that's the mean value, of the construction times has somewhat gone up and down over the decades, but in the past 30 years or so, it's been between 6 and 7 years. This is kind of compatible with the numbers from the proceedings article, which Naomi misquoted. This was the mean value, and as you expect, the median is lower than that. You can see this here. This figure shows the percentage of reactors that were finished within a certain time. You can see that this has a very long tail. The mean is 7.5, the median 6.3.
Okay, that's significant to consider. With the US in particular, a lot of the jobs used for that have been completely outsourced, and since the US hasn't built that many nuclear power plants in such a long time, there is a knowledge gap and a generation gap for new construction and just nuclear engineering in general. When I worked at the plant I worked at, it was, you'd have someone like me fresh out of college in my 20s, and then a lot of my coworkers were in their 50s and 60s, which, by the way, means, hey, a lot of those people, and some of them are still working now, are retiring. So if you want to get a job, then that's something to consider.
That's the global average, but there are big differences between countries. In Japan, the median time was merely 52 months.
That's fast.
That's about 4.5 years, so actually not that different from fossil fuel plants. Japan also holds the record for the fastest built nuclear power plant in the past decades. It took 39 months, so a little more than 3 years. In the United States, the median...
One of the reasons why that one in Japan was built so quickly was it was Unit 6. And what that means is they've already built 5 units at that site already, so they got everything into the groove, everything was pre-planned, everything was optimized about as well as you can. So they really saw some economies of scale with their construction time and with their processes. So that is one very viable thing. If you want to make a massive site, just adding on one additional reactor there, and usually they're built in pairs. I don't know the history behind that specific plant, but the even numbered reactor generally goes up faster than the odd numbered reactor.
It's 91 months. That's about 7.5 years. But in the 1950s, the American built nuclear power plants much faster, in one case in just 21 months. To summarize,
part of that is in the 50s, nuclear power plants were smaller in terms of megawatt output and in terms of size, and also in terms of how many additional safety features they had. Because 3 Mile Island hasn't happened yet back in the 1950s, which is the big accident that shaped all the industry in the US, that added a bunch of additional safety features, as well as create INPO, the Institute of Nuclear Power Operations. Started out as an NGO, but right now it's effectively an additional regulator, even though it's not technically a regulator.
It's true that it takes longer to build a nuclear power plant than to build a fossil fuel plant, and renewable energy power plants can be built even faster. But the difference isn't as big as some environmentalists claim.
This could also be reduced with small modular reactors. So think of that Eponese Fast example of having their Unit 6 up and running. Modular reactors can be built in a factory and then set up on site. So not only will that reduce this construction time, but it should also reduce the pre-planning time by quite a bit, which I know she's not including in this portion of her video, but that's a big factor that does take significantly longer for nuclear than fossil. Though it can take a while for fossil too, especially with new environmental regulations.
It doesn't take decades. It rarely takes even one full decade. Typically, it takes something like 6 to 7 years. The Japanese have done it routinely within 5 years. Contrary to rumors, the Japanese are also still using nuclear power and are even planning to build several new
home of the last meltdown
power plants. Let's then talk about costs. The cost for building a new nuclear power plant is typically 5 to 10 billion US dollars.
5's at the low end. I've seen north of 10, but again, mainly the main example that keeps coming is the one in Georgia, but she may be she's probably discounting the cost. She's probably not counting the initial appraisal costs and planning costs.
On the one hand, that seems like a lot of money. On the other hand, it's still less than Elon Musk paid for Twitter. Without context,
Wow, that's pretty good. Think about the positive effects on humanity here versus a Twitter or a tweet or an X or whatever those things are called versus safe, clean, reliable, sustainable energy source.
To tell if that's much or not. So here's the context. First, it really makes no sense to talk about the total cost of a power plant because some of them are larger and some smaller. It's like
you can. I mean, it's just a matter of scaling it per megawatt. That whole levelized cost structure has its own sort of problems.
Talking about the cost of wine without saying whether it's the price for a glass or a barrel. Therefore, when it comes to power plants, one usually talks about the cost per energy capacity or the cost per power that the plant eventually delivers. The units are then either dollars per watt hours or dollars per watt. If you're a particle physicist, then maybe you'd prefer something like Swiss francs per tera electron volt Fermi over C, but let's...
What? Oh yeah, because of that's where CERN is. All right. Also per watt hour, that's a very small unit to use for nuclear plants. Power used in a house is in kilowatt hours.
You look at something like the cost per bottle of wine. So for the plant, that's the cost per energy capacity. To get this number, you want to average over the entire lifetime of the plant and take into account the entire costs, both for the construction and operation. The result is known as the levelized cost of energy or levelized cost of electricity. Okay, now that we know what we're talking about, let's look at the numbers. The levelized cost of energy for nuclear power has been going up in the past decades. It's not controversial. Pretty much all sources agree on this. These are unsubsidized costs. Nuclear power is now 3 times as expensive as solar and more than twice as expensive as gas. So we see that, yes, nuclear power is more expensive than other sources of energy, but it's not hugely more expensive. It's not a factor 100, it's not even a factor 10, it's a factor 2 to 3.
2 to 3 is hugely more expensive. What? Okay. So yes, as that graph showed, it's highly susceptible to the cost of capital, just like any big project. And part of it is that reason is the associated risk of nuclear. Now, I'm not talking safety risk. Well, maybe perceived safety risk, but I'm talking investment risk. Because it's a longer-term project that is subject to changes of, say, who's in political office, and they may or may not want to consider, as well as it's just a long time to seeing the fruits of your labor, meaning the electricity that makes money. So investors are going to demand a higher rate of return, which is going to increase the discount rate. Now, for those of you who don't know what I mean when I say discount rate, I mean it's like interest rates, but you're going the wrong direction. Because nuclear power, you're not going to be producing it when you start this thing for, let's be optimistic and say it's 5 years. When you calculate that net present value, that higher rate of return every percentage point is going to hit you even harder, adversely affect the net present value, which is what you're going to look at when you decide to make an investment or not. It's unfortunate.
As a theoretical physicist, I'd say that's of order 1, so basically the same, really. You probably shouldn't leave your asset management to a theoretical physicist.
Yeah, that's probably right. There was certainly a lot to discuss in this video. Let's go ahead and call it a part for now. Thank you very much for watching. Stay tuned for part 2. Until next time.